screen okay?
Yes.
Yeah.
Fine. Yeah. So this lecture is to be considered in conjunction with what's called the Phelps carbohydrates video, which I'll give you the link for in the chat shortly. So many of the ideas talked about here are going to be reinforced by that video. And this is the last class of macromolecule we consider in the course. We already actually introduced polysaccharides a bit at the start of the course before we started to consider proteins. We've done proteins in some detail, nucleic acids in some detail, and now it's the turn of the polysaccharides. And having completed the basic physical chemistry stuff, molecular weight distributions, molecular weight averages, and non-ideality behavior, of course, but also in terms of conformations, we're now in a position where we can consider these interesting molecules, polymeric molecules, which can be highly charged, so negative charges here. And instead of a peptide bond in proteins, we've got these what's called glycosidic bonds between the carbohydrate monomer residues. This particular molecule is a molecule called alginate, which comes from seaweed and which has some very interesting applications, biotechnological applications. It's a copolymer. That means there's two types of residue, mannuronic residues, mannuronic acid and mannuronate residues, and also glyuronic or glyuronate residues. And you can see the different residues convey different local conformations along the polysaccharide chain. But more about that in a minute. In fact, I'll go to full screen mode. Can you all see that okay?
Yeah.
Yes.
And can you see my mouse key as well?
Yeah.
Yes.
Good. Right, so these are wonderfully diverse molecules with huge ranges of applications, and you'd be surprised where they turn up. You should look at the ingredients in, for example, toothpastes. They're very good at removing films of particulates, bacteria from the surface of your teeth, and they have also good rinsability. That means they will wash off afterwards when you have a mouthwash. So yes, definitely. Next time you go to the bathroom to clean your teeth, just look and see what polysaccharides you can find. Carrageenans, cellulose gum, xanthan, maybe alginate. You have a look and see what you find. They're also used as adhesives as well if you have to wear dentures and things like that. So, and yeah, and this is, anyone know who this is? No, it's Piers Brosnan. He was a former James Bond. I'm not sure, was he the last one before Daniel Craig? Oh, by the way, if you get a chance, you should go and watch the latest James Bond film. It's really good. It's the last one with Daniel Craig in. And Daniel Craig is from my part of the world as well, up in the northwest of England. So anyway, Pierre Brosnan is a former James Bond. Anyone work out the connection between him and this? Well, this is from the L'Oreal adverts. So one time L'Oreal used to get a series of stars in, Claudia Schiffer, Michael Schumacher before his injury, Piers Brosnan, of course, to model the use of this shampoo. And it contains a molecule called chitosan. And chitosan is a polysaccharide, which comes from mushrooms, also comes from the shells of crabs, lobsters, and other crustaceans. But these molecules are superb film formers, so they keep things in place, and that's why they're so good as shampoos. Another shampoo used in Weller, there used to be these adverts describing the Weller experience. Weller is based on arginates, which are also superb film forming polysaccharides. And with L'Oreal, Claudia Schiffer, Piers Brosnan, people like that say, because we're worth it, they're referring to the chitosan. That's just another example. If you want to find out more, then everyone recommends their own books, and I'm no exception, I'm afraid. So, An Introduction to Polysaccharide Biotechnology, published 2 or 3 years ago. This is the second edition, published with colleagues from health sciences here in Nottingham. Michael Toombs used to work for Unilever Research, now retired, and Berit, Kari, and Hilde are at the University of Oslo Department of Pharmacy. This talks about what it introduces polysaccharides and describes many of the wonderful applications of these types of molecules, including drug therapy and glycoconjugate vaccines against serious disease like meningitis. And then there's this other book which came from the Royal Society of Chemistry meeting on the stability of complex carbohydrate structures. So I can recommend these books, particularly if you go on to further research, if you're inspired to go on in further research into these types of molecules. Right. Anybody know who these gentlemen are here? Well, they both got Nobel Prizes for the work on working out the structures of carbohydrates. On the left is Fischer, Emil Fischer, who got the Nobel Prize in 1902 for producing the so-called Fischer structures. And Haworth, from the University of Birmingham, actually, got the Nobel Prize in 1937 for his work on the ring structures of carbohydrates. So these are the Fischer structures, linear structures for glucose and fructose. These have the same molecular weight, and they have the same chemical formula, but the arrangement of the atoms in the molecules are different, and therefore they are isomers, glucose and fructose. Glucose is an aldose, because of this group here, and fructose is a ketose because of this group here. But in nature, many, if not most, carbohydrates form ring structures, and these are the ring Haworth structures. And notice how the glucose, or glucopyranose, because it's a pyranose, six-membered ring with an oxygen in it. Many students forget to include the ring oxygen when drawing sugar structures. If they forget the ring oxygen, then they end up with probably a sugar alcohol, which is not normally the case. So don't forget the ring oxygen when showing the structures. This is the numbering of the carbon atoms: 1, 2, 3, 4. This is what's called the anomeric carbon atom, nearest to the oxygen on this side. 1, 2, 3, 4, 5, and then actually you've got this sixth carbon atom here. Whereas fructose forms a 5-membered ring, again with a ring oxygen, and the 5-membered or furanose ring. And depending on the orientations, now the way it's drawn here, it looks as if some of the atoms are above the plane of the ring and some are below. This is not strictly accurate, just the way we have to try and represent them. What the ones projecting upwards are axial, so the ones downwards are really equatorial. They're really in the plane of the ring structure. So axial and equatorial. And depending on, with carbon atom number 1, depending on whether the hydroxyl group on carbon atom 1 is equatorial or axial, dictates whether the glucose or glucopyranose is alpha or beta. The D, dextro, represents the way it rotates the plane of polarized light. So D and L-glucose are, I haven't shown L-glucose here, are mirror images of each other. But you'll see that in the Phelps video in a short while. If the position of the oxygen is changed on carbon atom 4, then you obtain a different type of sugar. If the hydroxyl group on carbon atom 4 is axial rather than equatorial, you end up with a monomer carbohydrate called galactose. So position can be very important in determining the properties and type of a carbohydrate. So these are the ring structures of glucose, of a pyranose, e.g. glucose, and a furanose 5-membered ring, e.g. fructose. And it's important to note that the ring structures themselves are not flat. Again, you'll see this in the Phelps video. So these are what's called the Chur conformations. So this is carbon atom number 1 here. So that, if you like, is the top of the Chur, and this is the bottom. And in this case, we start off with carbon atom number 4. 1, 2, 3, 4 at the top of the Chur. This is a 4C1 structure, and this is a 1C4 structure. So although we draw rings as planar structures, they're really not flat. And here's some of the nomenclature of carbohydrates. We use this 3-symbol notation normally, although that can extend to larger numbers of characters. Glucose, galactose is not glue, but GLC, lactose, gal, mannose, man, sorbose, fructose, rhamnose, fucose. It's very hydrophobic carbohydrate because it's methyl group. Ribose, xylose, arabinose, and then sialic acid, N-acetyl-neurominic acid, U5AC, N-acetyl-glucosamine, glucnac. And Phelps will refer to this in connection with blood groups. Galnac, N-acetyl-galactosamine, glucuronic acid, galacturonic acid, mannuronic acid, glucuronic acid. These are just some examples of monosaccharide nomenclature. And these come together via what's called the glycosidic bond, in parallel to what's called the peptide bond with proteins forming from amino acids. So you have disaccharides, ligosaccharides, polysaccharides, which you build on, which are built on the glycosidic bond, which have 2 degrees of rotation. These are the rotation angles of the glycosidic bond. If you have a 1,6 link, then you get an additional degree of freedom. This is the glycosidic bond, and this is where the 2 units can rotate. But of course, that rotation will be can be restricted because of the presence of other groups on the molecule, and it's these which underpin the flexibility of many polysaccharide structures. Here's a glycosidic bond. Basically, you have 2 OH groups coming together with the elimination of a water molecule, leaving a joining oxygen atom. And this is an example of a disaccharide. This is called Haworth structure of sucrose, which consists of a glucose molecule condensing or combining with a sucrose, with a fructose molecule. So it's carbon atom 1 of glucose linking up with carbon atom 2 of the fructose molecule. But there are many other examples in the book here, and also you'll hear more from the Phelps video. Then these can build up into larger polysaccharide structures, and you can get these repeat structures. So you get repeats of the same type of monosaccharide, all linking together to give a linear molecule, amylose, cellulose, punylan. So these are polymers of glucose, but linked in different ways. Then you can get what's called alternating repeat types of molecules, where you have one monosaccharide, then another, then another, then the other again, then the other one, in a regular sort of way. So molecules like agarose, and carrageenan follow this scheme. Then you can get these interrupted repeat types of polysaccharide structure. We have runs of one monosaccharide interrupted at different points with another residue. You get block copolymers, so you get blocks of one type of monosaccharide repeat, for example, glucuronic acid, and then blocks of another repeat, mannuronic acid, and blocks of another repeat. Could be glucuronic acid or mannuronic acid, or in some cases, alternating mannuronic and gluuronic residues. These are examples of a block copolymer polysaccharide. You can get branched types of polysaccharide structure, dextrans, malopectin, lignin. I think dextran is the subject of the assessment question which I've given you with different links. And then you can get these what's called complex repeat types of polysaccharide with different types of residues coming off at specific points. So these are the different types of repeat structures you can get with polysaccharide molecules. Here's an example of a complex repeat. This is xanthan. It's a beta 1,4-glucan with glucose residues linked together by beta 1,4 link. And then these side chains coming off, which can include these pyruvylated structures. So xanthan is quite an impressive molecule. It apparently forms double helices as well. And it's a microbial polysaccharide as well, with many interesting properties, largely based on its high molecular weight and thickening properties, very highly negatively charged, caused by these carboxylic acid carboxylate groups at normal pHs. And you can represent repeat structures with this type of notation, the 3-letter notation which I introduced in that table. So this is a popular way of representing the repeat structures of polysaccharides, or the primary structure of polysaccharides. In terms of conformations, these are these conformation zones again, which I introduced in the physical chemistry 4 lecture a little while ago. So this represents the wide range of conformation types we get with polysaccharides, generally far wider than we see with protein molecules. Zone A, extra rigid rod, for example, schizophyllan, which is a very rigid triple helical type of polysaccharide, also the evidence suggests. Then you get xanthan, complex repeat polysaccharide, because of its double helical properties and also its highly charged properties. Appears to adopt a rigid rod, but with some degree of flexibility, unlike schizophyllan. Then pectins, semi-flexible coil-like molecules, and then the random coils, dextrans and polylans, which have these very flexible flopsy types of conformation. Then you can get the highly branched types of molecules like amylopectin and glycogen, which can form a sort of more compact type of structure. So you get a huge variety of conformations with polysaccharides. And again, as we discussed in the previous lecture, using persistence lengths, where the persistence length is defined as the projection length along the initial length of the chain it's times projection along the initial length of the chain by dropping a perpendicular from one end of the chain onto the initial projection, in the limit that the contour length goes to infinity. So practically the limits are infinity for a perfect rod that has no flexibility at all, 0 for a perfect coil, perfectly random coil, which has no hindrance at all to the chain movement. So half the time it's in a positive direction, the other half in a negative direction. These like average out, so your net persistence length is 0, averaged over time. But practically, there's never an absolutely perfect rod or an absolutely perfect random coil. The limits for polysaccharides anyway are between 2 and 200 nanometers. So the very flexible molecules, random coils like plulam, have a persistence length like 2 nanometers, and schizophylam 150 to 200 nanometers. Very rigid molecule. And the semi-flexibles, 40, and then you get the more flexible molecules like these. So the persistence lengths are a very popular way of representing the conformations of polysaccharides. Now, finally, to go back to something we talked about right at the start of the course, which was the differences between proteins and polysaccharides. Now we've looked at the structures of these molecules in some detail. Now we understand the physical chemical properties. We can see that they're quite different with 1 or 2 similarities. Proteins are generally well defined. They are coded precisely by genes, hence are monodisperse. Whereas polysaccharides are often poorly defined, although some, as we've seen, can form helices, which give them some sense of rigidity rather than flopsy behavior. And they are synthesized by enzymes without a template, whereas proteins are synthesized by enzymes but coded by the genetic template. So these are very precise structures, highly monodisperse, single molecular weight. These are polydisperse and generally larger. With proteins, you have a standard peptide link, apart from proline, which is actually bent round on itself. So protein is an amino acid. So if you've got an amino acid, proline in the polypeptide chain, and actually what proline does, it produces a kink in the chain. But it's a peptide-like link. But generally speaking, between all the amino acids, apart from proline, you have a standard peptide link. Whereas in polysaccharides, it's the glycosidic bond. And with proteins, you tend to get a wide range of different residues in the protein molecule. With polysaccharides, it's the opposite. You get lots of polysaccharides are made of a one repeating residue only, and rarely do you get more than 3 or 4 different types of residue in a polysaccharide, unlike the 20 or so residues we find in a protein. And the difference is that the glycosidic bond has a variety of different links depending on which members of the different chains are coming together. For example, alpha depends on the position of the hydroxyl group on the anomeric carbon atom. It's axial or equatorial, and these are the various links that you can get depending on it's alpha or beta. And proteins, normally tightly folded structures and globular proteins, whereas polysaccharides, you get a huge range of structures from rods to random coils. Although it's worth pointing out that some proteins do not possess folded structures, and there's a lot of interest at the moment in what we call intrinsic disordering or denaturation of protein molecules, local denaturation, local disordering. And a classical example of a non-folded protein is gelatin, which has been described as an honorary polysaccharide. It's not a polysaccharide because it doesn't have glycosidic bonds, but in some ways it behaves like a polysaccharide in terms of its physical properties. And you can get some polyamino acids which compare or have behaviors comparing with some linear polysaccharides, but these generally are synthetic molecules, not natural. So that's a quick introduction to polysaccharides. You can reinforce that by referring to these books in the library. It covers, this one on the left covers the structures, and also on the many biotechnological applications of these types of molecules. There's some nice pictures there. There's also a picture of the use in encapsulation technology. So there's a lot of interest in polysaccharides in biotechnology at the moment, and also in biomedicine. I think I mentioned glyco vaccines. Okay, that's essentially it. Let's just come out of that. Close that. Right. So what can you see now, folks? Can you see me, or can you still see the screen?
Yeah, we can see you.
Okay, that's good. Any questions on that before we see the Phelps video? Latika, are you reasonably happy with that? Okay, so I'll do now then. We can have a chat after the video. I'll just stop sharing. So I stop recording now. Okay.